Hello, welcome to section 6.5, day 1, trigonometric form of a complex number. So we're going to look at the absolute value of complex numbers, and we're also going to learn how to graph them, and also look at the trig forms of complex numbers. So first, just to kind of start off and go back to knowing what a complex number is, a complex number in standard form is a plus bi, where the a value represents the real part of the complex number, and the b is the imaginary part of the complex number. And then, as a reminder, I is equal to the square root of -1. So the absolute value of a complex number is the distance between the origin and the point a comma b. So if I gave you the complex number -2 plus 3i, all right? -2 plus 3i, this is your real axis, which would normally represent our x-axis, and the imaginary axis would normally represent our y-axis. So -2, so we'd go 2 units to the left, and then plus 3i, we will go 3 units in the positive direction on the imaginary axis, and that creates this point right here. So this point would be -2 plus 3i. All right. Another way that you can actually write that, if we know we're talking about a complex number, is as an ordered pair -2 comma 3. But we have to understand that we're talking about a complex number when we write it that way. So if we want to find the absolute value of a complex number, we want to know what that distance is. So we have this distance in terms of -2 in the second quadrant, and then the positive 3. So -2 plus 3i. If we want to know what the absolute value of a plus bi, that's equal to the square root, it's the distance, Pythagorean theorem, the square root of your a value, which was -2, squared, plus the b value, not including the I, it's just the b, the distance, which is 3 squared. So this is, like I said, Pythagorean theorem, -2 squared is 4, 3 squared is 9. So the distance, or the absolute value, between those 2 points, or sorry, not between the 2 points, but from the origin to the complex number -2 plus 3i, is the square root of 13. So this would be the absolute value of -2 plus 3i, and that's equal to the square root of 13. So that's how you find the absolute value of a complex number. Math-wise, same math in terms of using the Pythagorean theorem, but now we're talking about the distance from the origin to that point, a comma b, for that complex number. So in the first example here, I want to plot the following complex numbers and then find their absolute value. So for point A, we have z is equal to -1 minus I. And z is just another way to write a plus bi. So if you look back on the first slide, I have z is equal to a plus bi. So once again, just another way to write that. So if z is equal to -1 minus I, we got -1 on the real axis and then -1 on the imaginary axis. So that point right here would be point A. And then if we wanted to find the absolute value, so the absolute value of -1 minus I is equal to the square root of -1 squared plus 1 squared. So the square root of -1 squared, well, -1 squared is 1, 1 squared is 1, which would just give us the square root of 2. So the absolute value of -1 minus I is equal to the square root of 2. Go ahead and pause the video and try B on your own. Alright, now that you've tried it, we got z is equal to -3i, so it's not, if you write this in terms of a complex number and you want to see both parts, it'd be 0 minus 3i. So we don't go left or right on the real axis, we didn't move at all, and then we go down 3 units. So this would represent point B, which is -3i. So your absolute value would be the square root of 0 squared plus -3 squared, and that is just 0 plus 9, or the square root of 9. So the absolute value of the complex number -3i is 3, which makes sense because the distance from the origin to that value would just be 3 units since you're not moving left or right. So that's how you plot points, complex numbers, and then also dealing with the absolute value of complex numbers. Now we're going to look at trigonometric form of a complex number. So this is used specifically when we're looking at powers and roots of complex numbers. So the complex number a plus bi, if we just kind of graph this in in one of the quadrants, we'll go ahead and graph it in quadrant 2. The a is this distance from the origin to that point, and then the b would represent this distance. So this point is a plus bi, and then this distance is that absolute value. All right. So if we're looking at this in terms of polar form, that distance would represent the r value, so the distance from the pole to the point, and then the angle would be this one, which would be theta. All right. So can we write a complex number in polar form? Well, yeah. We also know, remember from previous, that cosine of theta, and we can look at this one as well, cosine of theta is equal to the adjacent side, which would be a over the hypotenuse of r. So therefore a is equivalent to r cosine of theta. So we just saw that the other day. And then sine of theta is equal to b over r, where b is equal to r sine of theta. So if we know what a and b are in terms of polar form, then we should be able to take a plus bi as our complex number and rewrite it as a, which would be r cosine of theta, plus b, which is r sine of theta, and then don't forget the I at the end. Now we could factor out that r, and then that would leave us with cosine of theta plus I sine of theta. And right there is the polar or trig form of a complex number. So right down here you can see I have it written. So the trigonometric form or the polar form of a complex number is r times the quantity cosine of theta plus I sine of theta. Now, theta must be between 0 and 2 pi, including 0, but not 2 pi. The number r, sometimes we represent as what we call the magnitude or modulus of z, so that distance, and theta is the argument of z. So theta, once again, represents that angle that gets you to that particular point on the ray from the origin to the complex number. So if you hear that terminology, it still represents the two things in terms of polar form that we're talking about, the r, the magnitude or the modulus, and the theta is sometimes called the argument of z. So what if I ask you to write a complex number in polar form? Well, we did take rectangular form in terms of the point and convert it into polar form. So it's going to be kind of the same idea with your complex number. So we want to go ahead and graph, get an idea where it's at. So positive 2, negative 2. So we'll go 2 units this way, negative 2 here. So here would be the point 2 minus 2i. That would be a positive 2, and then this would be a negative 2. So we're looking for the r value and theta. Well, we can do that. Just like I said, we really did this the other day when we were going from rectangular form to polar form. So r would be equal to the square root of 2 squared plus negative 2 squared. So r is equal to 4 plus 4, or the square root of 8, which can simplify to 2 square roots of 2. So we have the r value. Now we need to know what theta is. We can now use tangent of theta, which is the ratio of y over x. So this would be negative 2 over 2, or negative 1. So where is tangent of theta equal to negative 1? But it has to be in quadrant 4. All right. So that would be the angle going in the positive direction, 7 pi over 4. So we have the r value and we have the theta. So now we know that 2 minus 2i as a complex number can be rewritten as r, which is 2 square roots of 2, times cosine of that angle, 7 pi over 4, plus I sine of 7 pi over 4. So those two things are equivalent. We have it in complex form, or a complex number, and then written in polar form or trigonometric form, same thing. All right, now I want you to go ahead and pause the video. I want you to do example 2b on your own. So use the same idea we just did. We need to find the r value and the theta, and then rewrite it in the correct form. All right, so hopefully you have now completed the problem. I found the r value. First I plotted the point so I could identify the x and the y, or the a and the b. And then I used Pythagorean theorem, or the absolute value for a complex number, to be able to figure out what that r value was. Came up with r is equal to 2. And then I used tangent of theta, which is opposite over adjacent, so square root of 3 over negative 1, or negative square root of 3. And since it's in quadrant 2, we had to make sure we got the correct angle in quadrant 2, which is 2 pi over 3. And then at the end, here is your complex number in polar form. Okay, I want to do one more with you, but I want to do one that doesn't have both parts. And so this is really 0 minus 3i. And so if we plot that, that's just 3 units down here on the imaginary axis. And we want to know what this distance is here, and then we want to know what the angle is. Well, we don't really have to do a whole lot of algebra here. You really can just think about it. What is that distance going to be? Well, the distance is going to be 3 units. We're going 3 units down. And then what is the angle going to be if we're going all the way around to here? Well, that would be 3 pi over 2. So you could still go through and do all that algebra, but once again, sometimes it's just easier to think about what it is that we're trying to find. So r would be 3. And then we have cosine of the angle, 3 pi over 2, once again between 0 and 2 pi, plus I sine of 3 pi over 2. And remember, this is equivalent to the complex number negative 3i. All right, and the last example I want to look at here is I want to graph, then write the complex number in standard form. So to graph it, your r value is 6, and your theta is 2 pi over 3. So just to kind of sketch this out, you would have this as your initial side, and then, or actually your polar axis, I should say. And then 2 pi over 3 is somewhere in this vicinity right here. So this would represent the 2 pi over 3. And then you would go 6 units out. 1, 2, 3, 4, 5, 6. And plot that point. So the point would be located approximately right there. Now, I also want to write the complex number in standard form. Well, if we want to get back to the a plus bi form, you're just going to work backwards, but the nice thing is that you know what cosine of 2 pi over 3 is. And then we're just going to be able to multiply that 6 through. So let's go ahead and see what that looks like. So 6 times cosine of 2 pi over 3, remember you are in quadrant 2, and pi over 3 has an ordered pair, just as kind of a reminder here. 1/2 square root of 3 over 2, but since it is in quadrant 2, it is negative. So cosine would be negative 1/2, plus sine would be positive square root of 3 over 2, and don't forget the I. And then you can just distribute the 6 through. So that would be negative 3 plus, the 6 and the 2 would cancel, so that would be plus 3 square roots of 3i. And so that is equivalent to all of that stuff up there. This is in complex form, where the original is in your polar or trig form. And so that is it. Once again, write your summary down. What are those important pieces that you need to take from this lesson?